NMR spectroscopy. This video is on the introduction to NMR spectroscopy. NMR spectroscopy is one of the powerful spectroscopic techniques used in the structural elucidation of organic compounds. It mainly identifies the carbon-hydrogen framework of organic compounds. Although NMR spectroscopy was developed by physicists in the late 1940s to study the properties of atomic nuclei, it was not until 1951 chemists realized the importance of NMR spectroscopy in the structural elucidation of organic compounds. Nuclei that have an odd number of protons or neutrons or both have a property called spin that allows them to be studied by NMR. Some examples of these include hydrogen, carbon-13, nitrogen, fluorine, and phosphorus. When it comes to the nucleus, we have to imagine the nucleus to be a tiny bar magnet. As a result of its charge, a nucleus with spin has a magnetic moment that is going to generate a magnetic field which is similar to the magnetic field that is generated by a bar magnet. Now, when you do not have any external magnetic field applied, the magnetic moments of these nuclei will be randomly oriented. But when you apply an external magnetic field, which is denoted by B0, the magnetic moments of the nuclei can align with the field or it can align against the field. Nuclei with magnetic moments that align with the field are in the lower energy state, also called as the alpha spin state, and those with magnetic moments that align against the field are said to be in a higher energy state, also called as the beta spin state. But remember, the beta spin state is at a higher energy level, and therefore more nuclei are said to be in the alpha spin state. And this energy difference between the alpha spin state and the beta spin state is called as delta E, and it is going to be directly proportional to the strength of the magnetic field applied. When a sample is subjected to a pulse of radiation whose energy corresponds to the energy difference between the alpha spin state and the beta spin state, the nuclei that are in the alpha spin state will get promoted to the beta spin state, and this process is called as flipping. NMR uses the radio frequency region of the electromagnetic spectrum to cause this flipping. Radio frequency region. Let's use some schematic representations to understand the principle behind NMR. Let's say that this is the nucleus and the magnetic moment of which is oriented in this direction. Now, when you apply an external magnetic field, this nucleus is going to get aligned with the magnetic field, which we generally call as the alpha spin state. Now, when this sample is subjected to a pulse of radiation, whose energy is going to correspond to the energy difference between the alpha spin state and the beta spin state, this nucleus from the alpha spin state is going to get promoted to the beta spin state. And this process is called as flipping. And the energy that is required to do this flipping is going to come from the radio frequency region of the electromagnetic spectrum. It is basically the RF frequency. And when the nuclei absorb radio frequency radiation and flip their spins, they're going to generate signals with frequency that is equivalent to the delta E, which is the energy difference between the alpha spin state and the beta spin state. The NMR spectrometer then detects these signals and plots their frequency versus intensity map, and we call that plot as NMR spectrum. Since the nuclei are said to be in resonance with the RF radiation, we use the term nuclear magnetic resonance spectroscopy. Difference in energy between the two spin states, namely the alpha spin state and the beta spin state, is going to be dependent on the operating frequency of the spectrometer, which is given by the equation delta E equals h nu, where nu right here is going to represent the operating frequency of the spectrometer. So this is operating frequency of the spectrometer. And this operating frequency is directly proportional to B0, which is the applied magnetic field, where H right here is going to represent the Planck's constant and gamma right here is going to represent the gyromagnetic ratio of the nucleus. So this is gyromagnetic ratio, and gyromagnetic ratio is a constant and it depends on a particular nucleus. For hydrogen, this value is going to be 2.675 times 10 to the power of 8 Tesla raised to the power of minus 1 and S raised to the power of minus 1. And for carbon, it's equivalent to 6.688 times 10 to the power of 7 Tesla raised to the power of minus 1 and S raised to the power of minus 1. Now let's say that we apply the gyromagnetic ratio and the strength of the applied magnetic field in this equation. So let's say that you're taking the hydrogen nucleus, for which the gyromagnetic ratio is 2.675 times 10 to the power of 8, and the applied magnetic field strength is 7.046 Tesla. So if this is the case, then the spectrometer will require an operating frequency of 300 megahertz. Therefore, if the spectrometer has a more powerful magnet, then it must have a higher operating frequency. For example, a magnetic field of 14.092 Tesla requires an operating frequency of 600 megahertz. Let's say that you're going to replace this number right here with 14.092. So you are increasing the applied magnetic field strength. So in which case, this number will get increased to 600 megahertz. So you need to have a higher operating frequency spectrometer. And because each kind of nucleus has their own gyromagnetic ratio, different frequencies are required to bring nuclei to resonance. Here is the frequency versus magnetic field strength table for different types of nucleus. As you can see from here, an NMR spectrometer that requires a frequency of 300 megahertz to flip the hydrogen nucleus requires a frequency of 75 megahertz to flip the carbon-13 nucleus. NMR spectrometers are equipped with radiation sources that can be tuned to different frequencies, so we can use the same NMR instruments to obtain the NMR spectra of different nuclei. Here are some NMR instruments which operate at different operating frequencies. The one that you see on the top left is basically a tabletop NMR spectrometer, which is generally present in an undergraduate laboratory. And here are some sophisticated NMR spectrometers which operate at a very high operating frequency. We now know that the strength of the magnetic field of the magnet that is present inside the NMR spectrometer is directly proportional to the operating frequency of the spectrometer. So if you're going to use the most powerful magnet, then definitely it is going to require a very high operating frequency. NMR spectrometers now range from 60 megahertz to 1020 megahertz. And here is the article that has been published in 2015, which has the world's highest magnetic field NMR spectrometer. And for that operating frequency, we definitely need to have a very strong magnet which has a field strength of 24 Tesla.